If you watch a lava lamp such as this one, you notice that there is material moving up and down. The wax at the bottom of the lava lamp heats up due to the energy from a light bulb. It rises to the top and it releases that energy, cools off, and then sinks back down to the bottom. This process occurs in the sun as well. And so in this mini lecture we're going to talk about how energy gets in and out of the sun. So here in the third mini lecture we are covering more of the material from section 16.2 and a little from section 16.7. And we learned in the last mini lecture that fusion produces energy in the center of the sun. If we want to see that energy here on Earth, that energy has to get out through 700,000 kilometers of the sun's radius. So how does that happen? The sun uses two different methods to get energy from nuclear fusion in its core out to the surface of the sun. For the inner 70% of the sun, if you remember from the first mini lecture, we call that the radiation zone. And that's because in this zone the sun transports energy using photons. Light created by the heat carries the energy outward. But this material is very dense, and just like if you are in a dense fog or trying to look through some dense smoke, the photon can't get very far before it runs into more material and it's absorbed again. That material then re-radiates the light as another photon in some other direction, and the photon, basically the energy tends to bounce outward, sort of like a model car, a toy car that runs off, hits the wall, turns around, goes another way, runs till it hits another wall, turns around, moves off another direction. Eventually it'll move further and further away from you, but it can take a lot of time. Another way of this type of process is sometimes called a drunk walk. You imagine that you've had too much to drink at the bar. 2 in the morning the bar closes, you need to walk home, and so as you start staggering home you don't really know what direction you're going, and so you'll walk until you run into a lamppost and kind of bounce off it, and then bounce off a newspaper stand and off the walls of the building, and slowly and surely you make your way further and further from the bar. Whether or not you make it home is another question. You might make it to someone else's house, but you move further away. Photons in the sun do the same sort of thing. They eventually move away from the core of the sun towards the surface of the sun, and this process takes an extraordinarily long time. Depending on the specifics of how you want to do your statistics, it can take energy anywhere from 30,000 years to 1,000,000 years to work its way from the center of the sun out to the edge of the radiative zone, 70% of the sun's radius. Now for neutrinos, which we learned in the last mini lecture, are also produced by nuclear fusion. Neutrinos can pass through almost a light year of lead without running into any of the atoms, without being absorbed. And so neutrinos can easily move through the 2.3 light seconds of the radius of the sun, and basically they zip on out of the sun as if there's nothing there at very close to the speed of light. So whereas it'll take the energy from a photon 30,000 or 1,000,000 years to get out of the core of the sun, the neutrinos make it out in 2.3 seconds. Now here on the Earth we have things called neutrino telescopes. This is a picture of a neutrino telescope in Japan called Super Kamiokanda, and what you have is this is a giant sphere far under the ground to protect it from radiation from space, and the sphere when it's active is filled with ultra pure water, and most neutrinos will go right through this water as if there's nothing there. But on rare instances, every few hours or so, one neutrino will interact with some of the water and release a little bit of light. The walls of the sphere are covered with very sensitive detectors that can detect even a single photon of light, and so the light created by the neutrino is picked up by one of these detectors, and then we know that a neutrino has entered the telescope. And we know we know very well what fraction of neutrinos that going through the telescope will actually produce light, a very small number. And so based on the number of flashes of light we see, we can tell how many total neutrinos went through the neutrino telescope, and we can compare that to how many neutrinos we think should be coming from the sun. And we find, when we compare our actual numbers to what we predict from the sun, that we get the correct number of neutrinos. Now, in your book, it talks about something called the solar neutrino problem, which used to be an issue that we detected fewer neutrinos than we thought should be coming from the sun. But several years ago, some scientists determined that neutrinos can actually change their characteristics as they're flying toward the Earth. And so we had to use a different set of characteristics for our calculations, and when we used that new set of characteristics, we found that the neutrino detectors are detecting the right number of neutrinos from the sun. This is very important because since we detect neutrinos coming from the sun, this proves that nuclear reactions are occurring in the center of the sun and that they're occurring still today. So we know for a fact that there must be nuclear reactions in the core of the sun because it's the only explanation for the neutrinos that we detect in these telescopes. Now, if you'd like a sense of scale of this telescope, on the right side of the telescope you can see a little rubber raft with a person in it, maybe 2 or 3 people, who are replacing some of the broken photodetectors in this neutrino observatory. So these are huge. There are several neutrino observatories worldwide constantly collecting neutrinos, and they are huge structures buried far underground. Outside of the solar radiation zone, so after the photons have taken 30,000, a million years to get from the core 70% of the way of the sun, the remaining 30% of the sun is what is called the convection zone. And the convection zone is very much like that lava lamp we saw earlier. Material of the sun, the gas that makes up the sun, near the bottom of the convection zone is heated by those photons coming up from below. And then the material begins to move, and it rises because it's hotter. It rises all the way to the photosphere, all the way to the very top of the sun, where it releases that energy. That energy streams off as the light that we see from the sun. When it releases the energy, the gas cools off and it begins to sink again, and it sinks to the bottom of the convection zone where it warms back up. So this entire convection zone of the sun is like a giant mixer, constantly mixing all the material in the outer part of the sun, constantly having hot bubbles rising, cold bubbles sinking. We can see this convection on the surface of the sun as something called granulation. If we look closely at the surface of the sun, we see these little granules, each about the size of the state of Texas, and they come and go, and we can even watch material moving in these. I've posted a link on eCollege with to a movie that shows this material rising up. It's an actual movie taken from telescopes on the Earth, and you can see the material bubbling upward, moving outward, and sinking again. So this solar granulation, which you need a big telescope to see, is caused by the convection of material rising all the way from low in the sun. So now that I've told you what's going on inside the sun, we've got the nuclear reactions that we know are happening because of neutrinos, but how do we know there's this radiation zone and convection zone? How do we know how deep they are? That's a nice hypothesis, but we always want to test our hypothesis. And thankfully, we have a way of testing it for the sun. The way that we know about the inside of the sun, first of all, as we've already mentioned, we can observe solar neutrinos. Second, we can make mathematical models. We take everything we know about physics and the composition of the sun and the size of the sun and the mass of the sun, and we put all of these into a computer, and it predicts what the structure of the sun should be. But again, this is a prediction, it's a hypothesis. We would like to test these models, and the way we do it is by observing vibrations in the sun. Let's talk about that a little further. So what are these vibrations on the sun? A very good analogy is the vibrations that happen on the Earth due to something like an earthquake. If we have an earthquake in Africa, the vibrations from that earthquake will move through the Earth and come out on the surface of the Earth somewhere else, such as Northern Europe. Or they might travel deeper into the Earth and come out on the other side of the Earth here in North America. Or they may travel along the surface of the Earth up to Europe. All these different waves traveling through are sampling different parts of the Earth. And so if we have a seismograph somewhere far away from the earthquake, we can detect these waves, and based on how long they take to travel through the Earth and how far through the Earth they've gone, we can determine what the interior of the Earth is like. And this is how we know the Earth has a solid inner core and a molten outer core and this layer of hot rock we call the mantle and the crust on top. This has all been done through earthquakes, which we call seismology. Well, we can use sound waves on the sun as vibrations that can travel through the sun to test the interior of the sun, and we call this helioseismology. So how does this work? The convection on the sun, the rising and the sinking of this material that we've learned about, produces sound waves. And we say, wait, I thought there's no sound waves in space. That's true. We cannot hear the sun from the Earth, but the sun is a dense gas like we have in our atmosphere, so sound waves travel through the sun just like they travel through Earth's atmosphere. So this rising and sinking of the gas produces sound waves, and the sound waves start to travel around the sun. Some go on the surface, some go down through, they go to different depths, and they come out on some other part of the sun. Now, if the sound waves are the right frequency, and frequency of sound is like a musical tone, if they're the right tone, then the sun will resonate like a bell at that frequency, and that frequency adds up and gets stronger. Other frequencies that are not the right tone will die away, and we won't see them on the sun. So the sun will ring in very specific tones, and we can watch on the Earth and see the sun vibrating at these frequencies. They reinforce. The sun rings like a bell at several different frequencies. We can detect those frequencies on the Earth, and which frequencies are there tell us about the sound waves that have gone through the sun and come up on the other side. And through some fairly complicated but completely valid math, we can determine what the interior structure of the sun is like. So here are graphs showing, let's start at the top. These two graphs show the temperature of the sun and the density of the sun as a function of radius, percent of the way to the outside. And the red dashed lines are our mathematical models. The orange lines are the helioseismology data showing the structure of the sun, and basically these two are indistinguishable. On this scale, we cannot tell any difference between our predictions and what is actually there, which tells us that we're predicting the right thing. The bottom graph shows another way to view this. It shows the percent difference between the model and the data, and what you see is that throughout most of the sun, the model is really close to the actual data from the sun. The only change is right here at about 70% of the sun's radius. That's where we have a difference. That's saying the models are not matching the data, although it's really close. You see it's 0.4% different. So 4 thousandths difference. That's a very tiny amount. And this 70% distance corresponds to the interface between the radiation zone of the sun and the convection zone of the sun. So what we learn from this is that we understand the sun very well, with some slight exception at this boundary between where the sun is moving energy by radiation and where it's moving energy by convection. So in summary, the sun transports energy from its core to the surface in two ways. For the inner 70% of the sun, it transfers it by radiation, by photons bouncing around and slowly working their way outward. It takes them several thousand to a million years to work their way from the core to the edge of the radiation zone. At the edge of the radiation zone, the sun begins to transfer energy by convection, by the motion of material, hot material rising to the surface, releasing its energy as light, cooling off, and then sinking back again. We can test these models of the sun in at least two ways. In the first way, we know that fusion is going on at the center of the sun because of neutrinos. These neutrinos are escaping the sun at the speed of light. They don't see all the material in the sun, and we're detecting them here on the Earth in special neutrino telescopes. So this is proof that there is nuclear fusion going on in the center of the sun. The other way we test our models of the sun is by this thing called helioseismology. Sound waves travel through the sun and sample different material at different layers of the sun. Which sound waves can make it through tell us about the sun's interior, and through analyses of this we find that our mathematical models of the sun match the actual structure of the sun very well, with a slight exception at the boundary between the radiative zone of the Sun and the convection zone of the Sun. So this completes our lectures, our mini lectures on the Sun, and you can now go and complete the response to the mini lectures and continue on in the work.